Hi students, welcome to my channel. Today's class, in our wave optics chapter, we can discuss about the resolving power of an optical instruments. Yes sir, resolving power of an optical instruments. Resolving power of an optical instruments. Okay, resolving power of an optical instruments. In resolving power of an optical instrument, first we should know about what is meant by resolving power. Yes, sir. What is meant by resolving power? Resolving power means that will be simple. It is an ability. It is an ability of an optical instrument. Ability of an optical instrument to produce distinctly separate images of an two closely lying objects. Two closely lying objects. Two closely lying objects. This one we are going to call it as what? Resolving power. Yes, sir. Resolving power. Now, resolving power RP, resolving power is inversely proportional to the limit of resolution. Limit of resolution. Resolving power is inversely proportional to the limit of resolution. That's the limit of resolution. I will explain what is the resolving power and limit of resolution. I am going to draw the diagram and I will explain. Just observe the properly definitions. What is meant by resolving power means it is the ability of an optical instrument to produce the distinctly separate images of a two closely lying objects. Yes, two closely lying objects. Now, what is meant by definition? Limit of resolution. Limit of resolution. Yes, no, limit of resolution means the minimum distance. The minimum distance between two objects. Minimum distance between two objects whose images just resolved by an optical instrument. Resolved by an optical instrument. Resolved by an optical instrument is called limit of resolution. Yes, it is called limit of resolution. Okay? Resolving power, another one way. Resolving power is inversely proportional to limit of resolution. Limit of resolution means the minimum distance between two objects whose images just resolved by an optical instrument. See, how to explain the concept of resolving power means simple. I am going to take one simple example. Say I am going to take one picture. Okay, this will be a picture. In this one, I am going to take one object. For example, I am going to write like this. When I am going to see this one, it is going to appear like a single picture. Okay, it is going to appear like a single picture. Now this one, I am going to enlarge. Means I am going to make bigger. I am going to make bigger. Means how is going to appear? Is going to appear like this. Again, I am going to make still more bigger. How is going to appear? Is going to appear like this. Yes, sir. This one. Now I am going to resolve. Means I am going to resolution. This is magnification. Magnified magnifying. Yes or no? Magnifying the picture. Now I am going to resolve. When I am going to resolve, what will happen? Resolution. Resolve means resolution. When I am going to resolve, what will happen? Say, this will be O. Is going to produce like this. Again I am going to resolve. What will happen? Is going to look like this. Say, in this process, magnifying means what? Making bigger. Magnifying means it will be making bigger. Resolution means what? Separating the object, two closely lying objects. Sorry, any closely lying objects, what we are doing? Separating. Yes, we are separating here. Distance between the objects will be small. Here, distance between the objects will be greater. Yes, distance between the objects will be greater. This one only we are going to call it as what? Limit of resolution. The minimum distance between the objects whose images are just resolved by an optical instrument. Yes, just resolved by an optical instrument. Here resolved means nothing the meaning. We are going to separate the images. Yes, we are going to separate the images. Yes, here single image. What we are doing? Separating. Yes, this one we are going to call it as limit of resolution. Yes, limit of resolution. The minimum distance between the two objects whose images are just resolved. Yes, these images are just resolved by an optical instrument is called what? Limit of resolution. The resolving power is inversely proportional to limit of resolution. Means this will be simple. The ability of an optical instrument. The ability of an optical instrument to produce the distinctly separate images of a closely lying objects. I think you people got the idea about what is meant by resolution and what is meant by resolving power. Here resolving power will be less, here resolving power will be more. Here because the distance will be more. Yes, the distance will be more. Now here, you have to remember one note points. The resolving power of an optical instrument like microscope and telescope is going to term as geometrical resolution. Okay, the resolving power of an optical instrument like microscope and telescope are going to term as geometrical resolution. Same way, the resolving power of an spectroscope is going to term as spectral resolution. Yes, no, spectral resolution. Then one more mark, or CET point of view, it will be very, very important. The limit of resolution of a human eye. The limit of resolution of a human eye is 1 minute. 1 minute or 0.1 mm, 0.1 millimeter. Human eye, 0.1 millimeter or 1 by 60 degree. 1 by 60 degree. This is what? Limit of resolution of a human eye. Yes, human eye. You have to keep in mind, the limit of resolution of a human eye is 1 minute or 0.1 mm or 1 by 60 degree. Yes, 1 by 60 degree. This is what? Resolving power of an optical instrument. The resolving power is always inversely proportional to limit of resolution. Meaning limit of resolution is the minimum distance between the two closely lying objects. Now, we can discuss about resolving power of a microscope and telescope. In your syllabus they mentioned microscope and telescope. Now we can discuss about resolving power of a microscope and telescope. resolving power of a microscope. Yes, resolving power of a microscope. Now we can write the definition. First we can write limit of resolution of a microscope. The limit of resolution of a microscope. The limit of resolution of a microscope means that will be simple. The minimum distance between 2 point objects. Yes or no? Minimum distance between 2 point objects at which they can be just resolved by a microscope. The minimum distance. The minimum distance between 2 point objects. The minimum distance between 2 point objects. Yes, a microscope. Yes, we are going to discuss about what? Microscope. The minimum distance between the 2 point objects at which they can be just resolved by a microscope. By a microscope. Yes, no, by a microscope. So here, this is what the minimum distance between the 2 closely lying point objects. Here, now what I am going to do is, now we have to write the limit of formula for limit of resolution. Means I am going to take 2 point objects, 2 closely lying point object. Microscope means what? We are going to take the objective lens. Objective, here there will be objects. When I am going to see from here, what will happen? Rays from here. This is the angle subtended, semi-vertical angle you can say. Okay, this will be the semi-vertical object, semi-vertical angle. Yes, no, semi-vertical angle. This is what? Objective of the microscope. Yes, no, objective of the microscope. Objective of microscope. This is what? Objects. Clear? Now, the limit of resolution of a microscope. Limit of resolution of a microscope is inversely proportional. Is directly proportional to wavelength. Is directly proportional to wavelength. And inversely proportional to refractive index. Yes, is inversely proportional to refractive index of the medium surrounded by the object. Yes, refractive index of the medium surrounded by the object, and semi-vertical angle subtended. This will be 2 sin theta. 2 sin theta. This is for what? Non-luminous objects. Non-luminous objects. Non-luminous objects. For luminous objects, that will be limit of resolution is equal to 1.22 lambda divided by 2n sin theta. Yes, no, 2n sin theta for luminous objects. For luminous objects. This is for luminous objects. Clear? Yes, no, for luminous objects. Luminous objects. This 1.22 is there. No, this is the correction factor. This is the correction factor due to diffraction effects. Yes, no, diffraction effects. Simple. The limit of resolution of a microscope. Yes, no, limit of resolution of a microscope is directly proportional to wavelength. Is inversely proportional to. Yes, no, is inversely proportional to refractive index of the medium surrounded by the objective. Yes, no, surrounded by the objects. Here object is there, no? This medium surrounded with refractive index. Okay. Next one is inversely proportional to 2 times the semi-vertical angle subtended by the object and objective. Yes, an objective of a microscope. That will be 2n sin theta. This is for 1.22 for luminous object. This 1.22 is due to what? Diffraction, correction factor due to diffraction effects. This is for non-luminous objects. This is non-luminous objects. Okay, this is what wavelength. This is the refractive index, medium surrounded by the objects. Yes, medium surrounded by the object. The 2 sin theta is a semi-vertical angle subtended by the objective and object. Yes, an objective and object. Now we can discuss about resolving power of a microscope. Yes, resolving power of a microscope. Resolving power. Same definition. Here was what? Limit of resolution. Resolving power is inversely proportional to limit of resolution. Same definition. Okay, same definition you can keep in mind. The reciprocal of minimum distance. Reciprocal of minimum distance between 2-point objects at which they can be just resolved by a microscope. By a microscope means already we know limit of resolution. Resolving power is inversely proportional to limit of resolution. Same definition issued at reciprocal of means the resolving power is equal to 2n sin theta divided by lambda. This is for non-luminous. For luminous, resolving power is equal to 2n sin theta divided by 1.22 lambda. 1.22 lambda. This is what resolving power of a microscope. Yes, the resolving power of a microscope. In your exam point of view, there will be a 1 mark question or 2 mark question. They will ask how we can increase the resolving power of a microscope. Yes, resolving power of a microscope. They will ask. We have to increase the resolving power of a microscope. Means that will be simple. See here. RP, resolving power, is directly proportional to what? N, refractive index. N is what? Refractive index. Means by placing a material of high refractive index in the medium surrounded by the object. In surrounding medium of the object, what you have to do? We have to place a material of high refractive index. That is the one step. You have to increase the resolving power. For example, when I am going to place a oil of high refractive index in the surrounding object, what will happen? That type of microscope you are going to call it as what? Oil immersion microscope. Oil immersion microscopes. Note point, oil immersion microscopes. Okay, by placing a material of high refractive index covered by the object, means that is what? That type of, when you are going to place a oil of high refractive index, that is what? Oil immersion microscope. Means we have to increase the medium of high refractive index, one step. Second one, here wavelength is directly proportional or inversely proportional? Inversely proportional, no, by decreasing the wavelength of light. Yes, no, by decreasing the wavelength of light. Yes, no, by decreasing the wavelength of light. Clear? Yes, no, by increasing the medium of refractive index, otherwise by decreasing the wavelength of light. Yes, no, by decreasing the wavelength of light. That is the one step. Clear? Next one. Very, very important question. That will be next one. Here, this n sin theta is there, no? This one we are going to call it as what? Numerical aperture. Numerical aperture. N sin theta. CET point of view, they will ask find the numerical aperture of a microscope. They will ask. You have to keep in mind 1 N sin theta. Yes, N sin theta. Yes, N sin theta is the numerical aperture. This is numerical aperture. Next one, here ion immersion microscope is there now. Same way, UV microscope. Yes, same way, ultraviolet, ultra microscopes. Yes, ultra microscope. In ultra microscopes, in like here, what we are going to use? We are going to use the light of UV light. Ultra microscopes. Keep in mind note points. Ultra microscopes. Ultra microscopes. In ultra microscopes, we are going to use light as UV light. Okay, we are going to use the light as UV light, and objective is there. No, this objective is there. No, this objective is going to be used by quartz material. Quartz material we are going to use. That type of microscopes we are going to call it as what? Ultra microscopes. This one you have to keep in mind. What is meant by my two types of microscope? One will be ion immersion microscope, another will be ultra microscope. In the ion immersion microscope, just we are going to put a ion surrounding the object, ion refractive index. Okay, this is about what? Microscopes. Yes, sir. This is about what? Microscopes. Now we can discuss about telescope. Yes, sir. We can discuss about the telescopes. Here, the microscope you are going to use it to see what? Point objects. Telescope you are going to use it to see. Microscope just you are going to use it to see the point object. The telescope you are going to use it to see what? In school level itself, you people are very familiar. Telescope use it to see the distinct objects. Yes, sir. We are going to use it to see the distinct objects. Yes, sir. Distinct objects. Okay, see here, what I am going to do means I am going to take a telescope. I am going to take a telescope. There will be two distinct objects. Two distinct objects. When I am going to see the distinct objects, this one only we are going to call it as what? Limit of resolution of a telescope. Yes, no, there is a limit of resolution of a telescope. Yes, no, this is the limit of resolution of a telescope. Clear? This will be telescope. There will be two distinct objects. Yes, no, two distinct objects. We have to see the two distinct objects. Now, the minimum angular distance there, the minimum distance here. This is the two objects. This distance we are going to call it as what? Angular distance. Yes, the angular distance. The minimum angular distance between two distinct objects, at which two distinct objects at which they can be just resolved. They can be just resolved by an. Now we are resolved by what? Telescope. Resolved by a telescope. Resolved by a telescope. This is what we are going to call it as what? Limit of resolution. Yes, sir. Limit of resolution. Here, the limit of resolution of a telescope. Limit of resolution of a telescope. Limit of resolution of a telescope is also directly proportional to wavelength. This is directly proportional to wavelength and inversely proportional to diameter of the telescope. Yes, no, diameter of the objective of the telescope. Yes, no, diameter of the objective of the telescope. Yes, no, diameter of the objective of the telescope. This one proportionality constant we should remove is that what we are going to take 1.22 lambda. 1.22 lambda divided by capital D. This is 1.22 capital lambda divided by capital D. Lambda divided by capital D. There, point object, microscope, we are going to use it to see what? Point object, the telescope, resolving power of a telescope. The telescope used to see what? Distinct objects. Distinct objects. Same way, this d theta only we are going to call it as what? Limit of resolution. Limit of resolution. Same way, resolving power of a telescope. Resolving power of a telescope. The reciprocal of minimum distance. Same definition we have to come. The reciprocal of minimum angular distance. Minimum angular distance between two distinct objects at which they can be just resolved. They can be just resolved by an telescope. They can be just resolved by a telescope. This one we are going to call it as what? Resolving power. Resolving power. Now already we know that resolving power is inversely proportional to resolving power is inversely proportional to limit of resolution is inversely proportional to resolving power, means that will be capital D divided by 1.22 lambda. 1.22 divided by D divided by 1.22 lambda. Here, this is what? Limit of resolution and resolving power of a telescope. This is the resolving power of a telescope. Here also, they will ask in exam point of view how we can increase the resolving power of a telescope. How we can increase the resolving power of a telescope. Here, see here, we should know about is directly proportional to D, inversely proportional to wavelength. We are going to say by increasing the diameter of the aperture object or by decreasing the wavelength we are going to say. But in this one we can't say wavelength. We can't say by decreasing the wavelength. When you are going to see by the telescope, the wavelength of the light will be constant. We can't change. Nature wavelength we can't change. Wavelength of the nature light we can't change. Telescope means we have to say only increasing the diameter of the objective. Increasing the diameter of the objective. In case of microscope, we can say by increasing the refractive index of the material surrounded by the object, medium surrounded by the object, or by decreasing the wavelength in microscope. When you come to the telescope, only one point. Only one point by increasing the diameter of the objective in the telescope. Keep in mind. Difference you can keep in mind, otherwise you are going to lose mass here. When you are going to write a wavelength over telescope, you will definitely lose the mass. This is about what? Limit of resolution and resolving power of an optical instrument. Here there will be compulsory 2 marks question or 1 marks question will be fixed in your board exams. Clear? This is what? Resolving power and limit of resolutions.